So what we're going to have a look at is how we can use trigonometry to find the area of triangles when we don't actually know the perpendicular height of a triangle. And we're going to actually go through a bit of a process where I look for a quick formula that we can use, and that's what we're going to get to by the end of the video. But I encourage that you actually work through with me to understand where this formula actually comes about. So let's consider the following triangle that we've got here. We've got a triangle that's got an angle between two sides that's 49 degrees, and those two sides are 8 centimeters and 10 centimeters. Now, up until this point, we know that we can calculate the area of a triangle using half times base times the perpendicular height of that triangle. The perpendicular height being this height just in here of our triangle. So it's got to be at right angles to the base. And the problem here is we don't necessarily know the perpendicular height of the triangle. However, obviously we've done some right angled trigonometry, because you can see I've just formed two right angled triangles here, where we can start using our knowledge of right angled trigonometry to find that height for us. So that's what we're going to start with, is we would find this height here. So we've got a right angled triangle here. Let's start by labeling this right angled triangle. Our reference angle is the 49 degrees. Our hypotenuse is the 8 centimeters. Our opposite side is the side that we're looking for. And our adjacent side is not 10 centimeters. Be careful of that, because the 10 centimeters is the whole way across. But we actually don't know what that exact length the adjacent side is. So what we do know is our angle is 49 degrees. Our opposite is what we're looking for, which is just h here, and our hypotenuse is equal to 8 centimeters. So looking at this, we can see that we will need the sine ratio because we've got the opposite and hypotenuse. So that's saying that sine theta will equal opposite over hypotenuse, which when we substitute in, will show us the sine of 49 degrees will equal our opposite, which is h, over the hypotenuse of 8. And obviously we now need to rearrange to get h on its own. So we'd multiply sine 49 with 8. I'll just show that working out. So we're multiplying here by 8, multiplying here by 8. I'm going to write h equals here, but it's 8 times sine of 49 degrees. And we've just got to quickly put that into the calculator here to make sure that we get the correct answer. Now we've actually started introducing, by the way, looking at radians. It is very important when you're putting these into your calculator that you do check what units that you're actually in. So probably could have just rounded this to 6 centimeters here, but because I'm going to use this to calculate the height, I'll just go to a couple more decimal places. But we've now got the height of the triangle, the perpendicular height that we need. So what we can actually do now is we can go, well, the area is equal to half times the base times the height. The base of our triangle we used as the 10 centimeters. So this will be half times our 10 times the perpendicular height of, and this is approximately 6.04, which I'm just going to use whole figures here because it's basically 6, so 10 times 6 is 60, half of that is 30, so we're approximately 30 square centimeters as our area of this triangle. Now, obviously, we could follow this process and get the area of our triangle. However, what I'm interested in looking at is there a quicker way that we could have done this? In that, we first of all did this sine ratio to find the height, and then we plugged that into our area formula. Now, we can do this because we're using one formula to substitute into the other formula. So let's have a look at how that might work with more of a general example. So when we're dealing with triangles, we do have to think to ourselves, we could have an acute triangle like we've got just here, and we could have an obtuse triangle. Now I'm going to focus on the acute case first because we do need to consider both cases if we're going to try and come with a general formula. But if we've got an acute case like we had here, we know that we need to calculate the perpendicular height of our triangle. So if we know that we've got an angle, we're going to say that we've got the angle at C here. All right. This is something that's actually new too. We are going to label our triangles from now on in a bit of a different way. We're going to label them A, B, C, where our capital A, capital B, and capital C are going to be our vertices, and then opposite sides of them are going to be the lowercase, and that's going to represent our side lengths. So that's something that you're going to see from here out, is I'm going to label our triangles a little bit differently here. So we've got our vertice here, which is a capital, and then opposite the vertice will be the lowercase, and we're going to have an ABC triangle. Now, what I was just referring to here is I've made the reference angle that we have angle C, just for the sake of this. And let's just say we know this angle. How would we go about, if we had this right angle triangle here, how could we go about finding this length here? Well, what we're going to say is, let's pretend I knew what the hypotenuse of this triangle was. Let's just say I knew this side length here. And let's say I actually knew this side length here as well, but that side length's not as useful to us because I don't know what that shorter part of that would be. But this one is. And we seen that earlier because when we go and label this right angle triangle. So we've got the opposite of our reference angle here, hypotenuse of the reference angle here. We're using the sine ratio. That's something we noticed before. So we know that sine theta will equal opposite over hypotenuse, and we substitute our information here. Our reference angle here is C. So instead of sine theta, we're going to say sine of C is equal to our opposite side, which is the side we're looking for, divided by our hypotenuse, which we just labeled as B. Okay, so what we're trying to do here is we are trying to find the perpendicular height. We're trying to find the h. So we know to find that we're going to have to multiply both sides by b here to get the h on its own. And you can see that's what we did in our example problem before. So then we had, therefore, our h is equal to b sine of the angle, just there, the angle of C. And you can see that this is very similar to what we did over the right here, just here. Like, we used the sine ratio, we multiplied by the bottom of that, and we got our height. And what we did with that is we substituted it into our area formula. So let's have a look at what happens when we substitute that into our area formula. So our area is equal to half times base times height. Well, we've got to consider here, like, what is our base going to be? Well, if our height is here, our base is clearly this side length here, which we've labeled as lowercase a. So this is going to be equal to half times our lowercase of a times our height. But of course, we've got our height. Their height is b sine of c. So it's going to be times b sine of C. And of course, we could clean that up a little bit by saying, well, this is going to be half A, B sine of C. We don't have to put those multiply signs in there. And what we've actually created here is a quick formula that we can use as long as we know this reference angle and the two sides either side of it. Note that it can't be this side. That's something that's really important with this formula. It has to be the two adjacent sides to our reference angle. Now, obviously, we've considered the acute case. What if we have an obtuse triangle? We have to make sure that when we're creating a formula like this, that we don't create something that's going to work when it's acute, but, what happens when it's obtuse? Well, for an obtuse triangle, the height that we need is not within the triangle anymore. Yeah, it's just over here. So we've got to go, okay, well, if I know the angle at C, let's just say I knew this to be the angle of C. We'll put that in here. Well, the angle of the right angle triangle I can create out of this would be 180 degrees minus whatever this reference angle is. And that's what this is referring to. It's 180 degrees minus the reference angle of C. And what we can actually do here is we can go through what we did before and label our right angle triangle we've got here. So that'd be the hypotenuse here. Our reference angle of 180 minus C. So that's opposite of our reference angle here. We're assuming that we knew this angle, which means we know this angle. So we've got the same situation all of a sudden. You can kind of see that. If we know, as long as we know that side length there, we can use the sine ratio, sine theta, equals opposite over hypotenuse, except what we've got this time, it's the sine of 180 degrees minus whatever our reference angle is equal to the opposite, which is the hypotenuse, divided by the b, so the hypotenuse of the triangle. So we're in a similar situation. We need to get the height on its own. So we're going to multiply this by b, we're going to multiply this by b, and you can suddenly see here that our height is going to be equal to the b multiplied by the sine of 180 minus c, which is great. We've got our height. The only thing is, I'm looking at this going, well, when we got our height over on this side, our height was just b times the sine of c, where our height over here is b times the sine of 180 minus c. Very similar, but we've got this 180 minus c. However, if you think back to the unit circle that we looked at, our unit circle, see how well I can draw a circle here. Our unit circle, we learned that if we take any random point around it, so this is a point P here, that the x coordinate is going to be cos of theta, the y coordinate is going to be sine of theta. That's what we learned. All right, and obviously the y coordinate, if we wanted to find it, we would drag across to the y-axis over here. Now, obviously, this is when we create this line segment from the origin to point P. So the origin just in here to point P, we end up with forming a right-angled triangle. If you look at it, I drew the right-angled triangles before like this though. So you can see here that we've got the right-angled triangle here, and the cos theta is our x value, the sine theta is our y value. The thing is, if this is our angle, now this is going to be hard to draw just on what I've got here, but if this here is our angle of C, which I'm going to call theta for right now, we've got to think about what would 180 degrees minus our angle be? Well, if you think about this, 180 degrees from our starting point on our circle would go all the way around to here. But then we've got to minus our angle of theta. So it would be back over here somewhere. That's 180 minus our angle of theta. So we would end up over here somewhere, which would actually line up with the same point that we have over here. And this is really, really important because what that means is 180 degrees, oops, let me come back. Give me a sec. There we go. What this means here, and I can actually zoom up on this, what this means here is 180 degrees minus our angle here will actually have the same y coordinates as just the theta. So what that means is 180 degrees minus our reference angle, the sine of it, this is really important, the sine of it is actually just equal to the sine of the reference angle. So what I'm saying, let me just write this down so that way we can see it. We're saying that the sine of our reference angle is actually the same as the sine of 180 minus our reference angle. And that's really, really important here because what that means is when we've got the sine of 180 minus c, we can actually immediately say that, hey, we know this. We know that the sine of 180 minus c is the sine of c. They're the same number, they're the same value. So we've got the same thing at this point. And of course, when we go to calculate the area of our triangle, we'll end up substituting the same thing that we had over here. So we'll end up with the area being the exact same formula, this half AB sine of c. So what I've just sort of stepped you through here is a bit of a proof. We've found a shortcut method to find the area of a triangle when we don't know the perpendicular height, but we do know a reference angle and the two adjacent sides. That's what we've actually just found here. Well, let's test it out. Let's see if we got it right. So let's come back and have a look at, this is our rule that we're saying we've found. Let's go and have a look at our original problem that we had. Well, the first thing that we're going to need to do with our original problem is label the triangle. Now, I'm going to label the triangle with sides, the vertices C as our reference angle, just because my formula is written in that way. A and B doesn't really matter so much. That was B, wasn't it? Yep. Good. So we've got here our triangle with our reference angle. So the area is equal to half times our A value. Now, A value is 10 centimeters here, so times 10, times our B value, which is 8, times sine of our reference angle, which is 49 degrees. Now, we can use this as long as the sides that we know are the adjacent sides to the reference angle. So we plug this into our calculator, and it's going to be 0.5 times 10 times 8 times sine of 49, and we get an answer that is just over 30, but is approximately 30 square centimeters, which when we look at what we had before is the exact same. So I guess what we've learned here is we've got now a shortcut method to find the area of a triangle, where as long as we know a reference angle and the two adjacent side lengths. And this is quite a lot easier to do than going through all of this process just to be able to do the area afterwards. And that's the reason why we do it. So essentially we've got this area formula. This here on this screen is what you need to be able to do with it. But understanding where it came from can really enhance your, knowledge of trigonometry as a whole.